Alright guys, so I'm gonna do a little learning session on quantum mechanics because I'm sick and I'm bored. I don't feel like doing schoolwork because it's easy. So the first thing we're gonna be learning about is standard model because it's the standard model. So these things here, quarks, um, they make up elementary particles like protons and neutrons, so they're kind of like pretty important. But you have like the up, the top, down, like you just have all the things there, and then you have electron. These things, I mean, electrons. You know what electrons are? They orbit atoms, nuclei, and that's basically an electron. Uh, they can appear in the middle of a nucleus if they quantum tunnel inside. And then we have the muon. That's an enlarged electron, which sort of just like is bigger and less stable, and then the tau is a bigger muon and less stable. You could sort of see here, like if you can interpret that. And then these are just, so this is the an electron, but it doesn't actually touch stuff. Like, well, it does, but it goes through it a lot easier. And then you have gluons. They like stick atoms together, I'm pretty sure. Photons are like light beams. These two are just, they're gauge bosons, so they also make up atoms, I'm pretty sure. This is a Higgs boson. Now, I'm not actually good at this, so yeah, that's probably a trash explanation, but you sort of get an idea of what it is. And the next thing I'm going to talk about is the Schrodinger's cat, because I have to be pretty typical about my quantum mechanics approach, and unless you've been living under a rock for the last decade, you probably have heard of him, and you've heard of this if you have any interest in quantum mechanics. Like, this is not something that's very hard. This is a box, and you have a cat inside. I can't draw a cat because I'm handwriting, but uh, in if you have a 50% chance of a bomb inside that will kill the cat, then you you press the button that activates 50% switch. It'll create two multiverses that have one where the cat is dead and one where it's alive, but it's in the superposition where it's in both dead and alive states. So basically what this means is that until you open the box and actually observe it, it's going to be dead and alive. And then it will choose either one superposition and take that. This can also be applied to like subatomic particles. They exist in both states until you actually observe them, and they choose one. That's also how quantum computers work. So they'll exist in like both states, of both a 0 and 1, which is why it's called the qubit. And then once you observe it, it goes in either one. So it sort of takes the it sort of takes the state that it wants to, which makes it a lot easier to compute because it's how quantum computers work. Anyway, I'm not going to explain that too much. It's not that important. Second thing is probably the Heisenberg uncertainty principle. So it's basically when this dude called Heisenberg was uncertain. Well, actually, what it was is that basically it's a fundamental limit. I think the equation is like something like that. And it's basically you can't when something's moving, there's like a limit for how much accuracy you can have for a particle. So you have someone running, you can't figure out both their position and their speed at the same time you can only observe either one because of quantum mechanics. Let me think about this. This is probably just weird. So my brain's just small, and all you have to know about this is that Heisenberg said some stuff that you can't measure. It's both the speed and the whatever of an atom. The speed and the space it's on at the exact same time of an atom. Now the next thing I'm probably going to talk about for quantum mechanics is the multiverse theory. You've already heard about this because I said it earlier, but what the multiverse theory is that every time there's two events, this is a bit like Schrodinger's cat, it splits a multiverse which creates two multiverses, and there's infinite amount of multiverses where there's infinite amount of times that you are repeating the exact same thing. All of them can have different laws of physics and different things. One of the explanations for why the universe has got perfect conditions for life and everything, 3 dimensions, you know, it's disputed that there's 11 dimensions because it would be like for string theory to work, you need 11 dimensions for the math to work out. And string theory is basically that all electrons and stuff, all those particles I showed at the start that I didn't actually really know very well, are actually strings in a circle, and they've got different string lengths and wavelengths. And then black holes are basically just those strings like stretched out in a circle. This is a bit off topic from multiverse, but say this is a black hole. Oh wow, that's black. Oh no. Okay, yeah. It's just a bunch of strings. Like, let's just draw some strings in green because that's how they do it in all the videos. That's a black hole, and inside, I'm just gonna dye it red because there is where space-time stops. So it's sort of space-time goes like this if string theory is true, and this is the thing of black hole. Okay, that's not a very good diagram. Well, this is like inside the black hole, and this does not exist. This is like space outside, but it doesn't technically exist in the space-time continuum because otherwise that means that it's got a singularity of infinite density and 0 mass, which is a bit sus. So this explains a bit of things, but it's also sus, so it's probably a bit wrong. Now the next thing I'm going to talk about is relativity, because I don't know, just quantum mechanics is bullying me. So, here we go. I'll just delete all this because I actually am kind of annoyed with quantum mechanics now. It's a bit annoying, and I'm sick, so I forgot it all. But I can use my sickness as a bit of an excuse of being stupid. Anyway, so this is a graph. I don't know if you've ever seen a graph before. I haven't. But if this is the speed of space-time in like a constant, you know, gradient, m equals 1, you did this in kindergarten, coordinate geometry. You know that like every point on this graph is going to be a point on the graph with the gradient m equals 2 equals whatever e equals. I think it equals like 1. Let's just say it equals 1. Like if you go faster, it looks like that because time slows down when you go faster. And gravity is actually a geodesic, guys, according to Einstein. Yeah, we're traveling on a geodesic. Gravity's a lie. Newton did some fake news. And it's time for me to do some integral calculus, boys. Now, hopefully you learned something from this video. I know I didn't, but you probably didn't either.